Hello. If you are watching this video, that means you have watched the 2 hours of content I made on Unit 3. Again, sorry for making it so long. Didn't realize that was happening, but I wanted to be thorough. We went through everything in Unit 3. So now we're going to go over the progress check. I'm going to take it right now. I have it in preview mode on my computer, so I'm going to go through all of the multiple choice questions, and I do have the answers in another tab, so we'll go back and forth. I will answer each question. I'll explain my thinking on each question. I may get some of them wrong. All right, if we get one wrong, we'll figure out why the correct answer is the correct answer. All right, so let's just dive in. Question 1, we have diagram 1 and diagram 2. It kind of looks like cooties. I don't know if anyone ever played that game. It was a game I had as a child, but so we're looking at a molecule. The black is C, so it's carbon, carbon, oxygen. Oxygen is bonded to the hydrogen. This is where having a little bit of an organic chemistry background is pretty good. This is 2 carbons is ethane, the oxygen, then the hydrogen like that. It's an alcohol group. This is ethanol. So which particle diagram shown above best represents the strongest intermolecular force between 2 ethanol molecules? All right, it's gonna be between the OHs, right? The carbon-hydrogen bonds, those are weak nonpolar covalent bonds. They're going to have LDF as their strongest intermolecular force. This is a relatively small molecule. It doesn't have that many electrons, so not very polarizable. So we're going to get the hydrogen bonding here between the hydrogen and the oxygen. All right, partially positive, partially negative. The hydrogen will be attracted to the oxygen of the other one. So the answer is going to be diagram 2. We have 2 choices, choices C and D. Diagram 2, because it shows the formation of hydrogen bonds between an H atom bonded to an O atom with an O atom from another molecule. Or choice D, diagram 2, because it shows the dipole from an ethanol molecule, including a dipole in another ethanol molecule. Choice C mentions the hydrogen bonding. I like that choice. Let's see if it's correct. Choice C. Wahoo! All right, question 2. So we have lithium plus, Mg2 plus, sodium plus, calcium 2 plus, and we see their relative sizes. Period 2 on the periodic table, period 3. The diagram above represents 4 cations, all shown to the same scale. Which cation would be predicted by Coulomb's law to have the strongest ion dipole attraction to water, and why? All right, Coulomb's law. The force of attraction is equal to Q1 times Q2 divided by R squared. The larger cations are going to be important. And when I say larger, I mean the charge. So it's either magnesium or calcium because they're 2 plus. And how close the water molecules can get to it will matter. Because the magnesium ion is smaller than calcium, it's going to be Mg2 plus because it has the largest charge to size ratio. So for question 2, it should be choice B. Question 2, it's B. Wahoo! Hope that doesn't get old. All right, question 3. A solid compound of a group 1 alkali metal and a group 17 halogen element dissolves in water. The diagram above represents one type of solute particle present in the solution. Which of the following identifies the solute particle and best helps explain how the solute particle interacts with water molecules? All right, so this is either the alkali +1 metal or the halogen -1 anion. Now, we see the water molecules around it. Now we know this is the oxygen. It's bigger and there's only one of them. The oxygen is near it. The oxygen has what charge? It's partially negative. So that means this must be positive. All right. The particle is a positive ion and the interactions are ion dipole attractions, or the particle is a positive ion and the interactions are dipole attractions. Well, this is an ion. These are polar molecules with permanent dipoles, so ion dipole attraction. So for question 3, this should be choice C. Let's double check it. Question 3, C. Wahoo! Question 4, allotrope 1, allotrope 2. All right, so allotropes, those are the same elements, but different forms of them. All right. The diagrams above represent 2 allotropes of solid phosphorus. Phosphorus, a non-metal. So that means that these are molecular. Which of the following correctly identifies the allotrope with the higher melting point and explain why? All right, this is an awesome visual. So allotrope 2, I see a lot of solid lines. All right, it's very neat, it's very organized, they're at fixed angles. This is a covalent solid. All right, we can get a covalent network solid. We can get that when we have our nonmetals. All right, so they are bonding in covalent bonds in all those directions. And covalent network solids have really high melting points, high boiling points, all that good stuff. Now, these are P4 molecules. So this is a molecular solid. They do have London dispersion forces between each other. By all means, a P4 does have a decent number of electrons, so it is fairly polarizable. So it's probably going to have a higher melting point than other molecular solids, but it can't compete with that covalent network. And we can see it, right? They're their own distinct molecules, whereas here we see that network, all right? And we don't see all those lines. So which of the following correctly identifies the allotrope with the higher melting point and explain why? It's going to be allotrope 2. Now we got to double check the reasonings. All right, so choice B, allotrope 2, because it has covalent bonds between the phosphorus atoms that are stronger than the dispersion forces between the P4 molecules in allotrope 1. I like that. Let's just check C though. Allotrope 2, because it has metallic bonding. Moo! Metallic bonding is not a metal. It's a covalent compound. No way can it be choice C. Do I even want to continue reading? All right, so for question 4, we're looking for choice B. Woohoo! All right, question 5. Okay, we got a lattice. That's the picture. We got a lattice, guys. No, don't get excited. It's just a lattice. All right, the crystalline structure of NABR is represented in the diagram above. Which statement correctly compares crystalline NABR to molten NABR in terms of electrical conductivity? All right, right off the bat, crystalline NABR not going to conduct any electricity, all right, because those atoms, they're kind of stuck in place, all right? Now, the NABR can conduct electricity when it's molten, when it's in that liquid phase, because the ions are free to move about, all right? So crystalline NABR contains no freely moving electrons that could conduct an electrical current, whereas electrons can flow freely in molten NABR, which is a good conductor of electricity. That's okay. Is it going to be our best explanation? We'll see. Choice B, crystalline NABR and molten NABR both contain ions that are held in fixed positions due to strong electrostatic attractions among the ions, making neither a good electrical conductor. Well, true for the solid, not true for the liquid. Crystalline NABR and molten NABR both contain Na atoms that transfer electrons to Br atoms in a chemical reaction. True, thus allowing them both to be good conductors of electricity. Not true. All right, and choice D, crystalline NABR contains no freely moving electrons to conduct electricity, but molten NABR is composed of free-moving Na plus and Br minus ions, which allow it to be a good conductor of electricity. All right, so we're narrowing it down to A and D. The electrons have already moved, so I don't really like how they're talking about the electrons freely moving. I think it's more so the fact that we have the ions, and the ions can move, which is going to do the current. So I'm going to go with choice D. All right, I have it narrowed down to A or D. I'm a little nervous. We'll check. We'll see what happened in question 5. Choice D. Woohoo! All right, choice A was close, but the explanation was just a little bit lacking. All right, and the other thing I would mention, choice D just gives us a little more detail, and it has some true information. We know it's Na plus and Br minus ions, right? So, you know, the freely moving electrons, that's not really something we've ever talked about with ions. So let's not think about that. All right, question 6. Ooh, I got my diamond, I got my graphite. These are both carbon, all right? These are both covalent network solids. You need to know those two, because those are like the two that are always talked about, right? Diamond versus graphite. So you should already have an idea of what's going on in this question. You should be able to visualize both of these. The structures of two allotropes of carbon, right? And again, allotrope just means that it can have different forms, even though it's the same element, are represented above. Which of the following statements best helps explain why diamond is much harder than graphite? All right, it's much harder. Diamond contains covalent bonds, where graphite contains ionic bonds. That's incredibly inaccurate. Come on. Diamond contains ionic bonds, whereas graphite contains covalent bonds. So A and B both false. There's no ionic bonds going on at all. C, carbon atoms in diamond have 4 covalent bonds, whereas graphite is made of layers that are held together by relatively weak dispersion forces. Well, the carbons do have 4 bonds, and the graphite does form layers. Now, choice D, carbon atoms in diamond have a sea of mobile electrons. That's metallic bonding. They're really going to try to throw metallic bonding at us when we clearly have a covalent network solid. All right, it's going to be choice C. Question 6, we're looking for C as our answer. Wahoo! Question 7. All right, so a gaseous air-fuel mixture in a sealed car engine cycle has an initial volume of 600 ml at 1 atmosphere. To prepare for ignition of the fuel, a piston moves within the cylinder, reducing the volume of the air-fuel mixture to 50 mLs at constant temperature. Assuming ideal behavior, what is the new pressure of the air-fuel mixture? All right, so the volume's being reduced from 600 ml to 50 ml. So I believe it's being reduced to, that would be 1/12 of its initial volume, right? So the volume is being reduced. So now the pressure is increasing. So 600 to 50. So since the volume's going down, pressure's going up. Boyle's law. All right. So, it gives us numbers. About 0.083. Nope. Pressure has to get bigger. All right. About 120 atm. That's, I think, a bit too large. About 550. All right, choice B, about 12 atm, because the volume of the gas mixture decreased by a factor of 12. All right, so volume decreases by 12, pressure increases by 12. Let's double check question 7. All right, 12 atm. Wahoo! Question 8. At 10 degrees Celsius, 20 grams of oxygen gas exerts a pressure of 2.1 atm in a rigid 7.0 liter cylinder. Assuming ideal behavior, if the temperature of the gas was raised to 40 degrees Celsius, which statement indicates the new pressure and explains why? All right, you are welcome to work this through with calculator. I'm going to try to rationalize it without a calculator. All right, so we're going from 20 degrees Celsius to 40 degrees Celsius. So we are quadrupling the temperature. Psych. All right, you got to add the 273. We're only slightly increasing the temperature, right? It's not quadrupling. It's going from 283 Kelvin to 313 Kelvin. So it's only going up a little bit. And we're going to keep it in a rigid 7-liter container. So the volume's not going to change. The number of moles isn't going to change. So all that's going to increase is the pressure. If the temperature goes up, the pressure will go up. All right, we're at 2.1. So we want to just pick something that's going to slightly increase. I like B, 2.3 atm. All right, a little bit of a shot in the dark. All right, because it's increasing by the portion of 313 over 283. That makes sense, right? That would be the initial temperature over, so they're working through. So for question 8, we're going with choice B. Oh, there it is. Wahoo! All right, question 9. Ooh, look at this diagram. All right, oxygen pressure of 0.88 atmospheres, nitrogen pressure of 1.0 atmospheres, oxygen plus nitrogen. Is this really going to be a Dalton's law of partial pressures question? Is this really just going to be 1.8? All right. 2 sealed, rigid 5-liter containers each contain a gas at the same temperature but at a different pressure, as shown above. Also shown are the results of transferring the entire contents of container 1 to container 2. No gas escapes during the transfer. Assuming ideal behavior, which statement is correct regarding the total pressure of the gases after they are combined? All right, the total pressure of the gases in the mixture is the sum of the initial pressure of oxygen gas and nitrogen gas, because pressure only depends on the total amount of gas when volume and temperature are held constant. Sounds reasonable. B, the total pressure of the gases in the mixture is lower than the sum of the initial pressures of oxygen and nitrogen, because some of the energy of the particles will be lost due to an increase in the number of collisions. Well, I don't know why the number of collisions would decrease the energy. All right, there could be more collisions inside, that's fine, but we're going to assume that they're elastic. The total pressure of the gases in the mixture is higher than the sum of the initial pressures of oxygen and nitrogen, Because of the intermolecular forces that develop between oxygen and nitrogen molecules. Well, both of them have weak attractions to begin with, and if there were attractions, that wouldn't increase their pressure, that would actually decrease it, right? It would diminish the number of collisions on the walls. And then the total pressure of the gases in the mixture cannot be determined because the actual value of the temperature is not given. So, all right, I'm totally going with A on this one, right? Pressure only depends on the total amount of gas when volume and temperature are held constant. So question 9, we're looking for A. Wahoo! Ooh, this is tiring, guys. You know, wahooing every question. All right, question 10. Okay, we got two diagrams, diagram 1, diagram 2. The diagrams above use arrows to represent the speed of a gas particle. Which of the diagrams best represents the speed of the particles of a gas at a fixed temperature and why? All right, in diagram 1, it looks like they're all the same length. In diagram 2, it looks like we got a couple that are a little short, couple that are a little bit longer. All right, so we kind of have mix. All right, so our choice is diagram 1 because all the particles have the same speed. All right, choice B, diagram 1 because the particles are moving in different directions. All right, so between those two, the same speed looks better. The different directions, that doesn't mean anything. Gases are always in constant motion in different directions. Diagram 2, because the particles have a net kinetic energy of 0. That's weird because kinetic energy represents temperature. Diagram 2, because the particles have a variety of different speeds. All right, this is an annoying question. So where you want to go with it is going to be choice A, all right, because if they're all the same speed, they're at the same, they're moving at the same rate. But there's that Maxwell-Boltzmann distribution, and I think they're going to go with choice D. I think they're going to say that at a fixed temperature, not every particle is moving at the same speed. It's a distribution with only a couple of them moving faster, but we get it all spread out. So I'm thinking Mr. College Board's trying to trick us here at number 10. I think he's going with choice D. Let's see what happens. Yep, that's what he went for. All right, so it's a very annoying concept, but just keep in mind that when we're looking at a gas, even at a fixed temperature, that does not mean every particle is moving at the same speed. All right, it means that the average of all of the particles is going to be the same, right? That kinetic energy, but particles will be moving at different speeds. Question 11, we're about a third of the way through. Oh, look at that. That here is our Maxwell-Boltzmann distribution. All right, so we got gas X and we got gas Z, all right? Solid line, dashed line, percentage of molecules and their speed. All right, so it looks like more of gas X molecules are at a slower speed than gas Z. The two gas samples represented in the graph above are at the same temperature. Which of the following statements about the gases is correct? All right, the molecules of gas Z have, okay, wait, they're at the same temperature. That's a huge detail, right? That means they have the same kinetic energy. The molecules of gas Z have a higher average kinetic energy than the molecules of gas X. No, because they're at the same temperature. There are fewer molecules in the sample of gas Z than the sample of gas X. I don't think that's where they're going with it. Gas Z has a smaller molar mass than gas X. Well, if it had a smaller molar mass to have the same kinetic energy, it would have to move quicker, right? Because kinetic energy equals 1/2 mass times velocity squared. So if they were smaller, they would have to move faster. So I like choice C. Choice D, gas Z has a greater molar mass than gas X. That cannot be it, because if they had a greater mass and a greater speed, then they would have a greater kinetic energy. So for question 11, we're looking for choice C. There it is. Wahoo! Question 12, relative number of molecules and the speed. So we have distribution, but only for one. The diagram above shows the distribution of speeds for a sample of oxygen gas. Which of the following graphs shows the distribution of speeds for the same sample at a higher temperature? All right, higher temperature, it's going to shift it to the right. Think of it as like flattening the curve. All right, so this is actually a lower temperature, all right, which is why we have a lower speed and more of the particles at the lower speed. This also is shifted left. That's not going to work. All right, Choice C, we are shifting to the right, which means our average speed is moving to the right and we're kind of flattening it out. I like choice C. Choice D, while we're shifted right, it needs to go down a little bit too. It needs to be a little more spread out in these Maxwell-Boltzmann distributions. So it's going to be choice C for question 12, guaranteed. All right, look at that. You know what's going to happen. Woohoo! Question 13. Equimolar samples of CH4, methane, and C2H6, ethane, are in identical containers at the same temperature. The C2H6 deviates much more from the ideal behavior than CH4 does. Which of the following best helps explain this deviation? All right, why do gases deviate? Because of attractive forces. So as we look at it, C2H6 molecules have more hydrogen bonding than CH4 molecules do. Isn't that in my do not think that CH bonds are hydrogen bonds? Because they are not. C2H6 molecules have a larger, more polarizable electron cloud than CH4 molecules do. That sounds pretty nice, right? More polarizable electron cloud. That's just a good phrase to keep in your back pocket. The C2H6 molecules have a greater average kinetic energy than CH4 molecules have at the same temperature. So choice C is out. Choice D, the C2H6 molecules have a greater average speed than the CH4 molecules have. Actually, be the other way around. CH4 has the greater speed. So it's going to be choice B. Choice B was beautiful. All the other choices were so bad. All right, choice B. Wahoo! Question 14. The gases CO2 and NH3 can be liquefied at 20 degrees Celsius by compressing them to sufficiently high pressure. A student claims that NH3 gas can be liquefied at a lower pressure than CO2 gas can be liquefied. Which of the following is the best justification for this claim? All right, so the kid's saying NH3 doesn't require as much pressure as CO2. At 20 degrees Celsius, the average speed of NH3 molecules is greater than that of CO2 molecules because NH3 molecules have less mass than CO2 molecules. Well, that's true, but mass usually isn't the explanation for these types of things. It's not that different. Mass, 17 grams per mole versus, I guess a little bit different, but 44. All right. CO2 is a non-polar molecule that has no significant intermolecular forces, whereas NH3 has strong London dispersion intermolecular forces. Well, CO2 is definitely non-polar. The bonds do cancel out. And something with strong attractive forces, right, is going to liquefy a little bit easier. It's going to condense. Both CO2 and NH3 are non-polar molecules that have only London dispersion intermolecular forces, but the larger electron cloud of CO2 molecules causes it to have stronger intermolecular forces. Well, that would be true, but is NH3 non-polar? I think it's forming hydrogen bonds. All right, so choice D. CO2 is a non-polar molecule that has London dispersion intermolecular forces that are weaker than the dipole-dipole and London dispersion forces between the polar NH3 molecules. I think I like choice D, all right, because NH3 is a polar molecule, CO2 isn't. So since it's polar, it has stronger attractive forces from two different sources. So let's see if D is the correct answer for question 14. Yes, it is. Wahoo! Question 15. Okay, so we got the volume, we got the pressure. Our ideal gas is in the dotted line. Our real gas is off to the side a little bit. So what is this saying? At a high pressure, we're deviating more from the ideal gas, all right, which should make sense because at a high pressure, molecules are going to be much closer to each other. They're going to start interacting, all right? At low pressures, that's when it's going to be more ideal because they're going to be further apart. All right, the graph above shows how a particular real gas deviates from ideal behavior at very high pressure. Based on this information, which of the following is most likely the gas and gives the reason based on kinetic molecular theory? H2, because it has the smallest mass. N2, because its molecules have a triple bond. Ne, because it has a completely filled valence shell. SO2, because it has the largest molecular volume. All right. I would have loved to have seen something about polarability, how polar they are, but that's not coming up. SO2 is triggering in my head, though, that that's a polar molecule. And the molecular volume will be a reason for why we deviate from a real gas at high pressure. Because at high pressure, they're close to each other. And if something does take a up a little more volume. While that's not going to be dramatic at a low pressure, that could be dramatic at a really high pressure. So I'm going choice D for question 15. Choice D. Woohoo! I didn't see 16, so don't worry. All right, 16. What volume of a zero point 0.1 molar HCl stock solution should be used to prepare 250 mLs of 0.0250 molar HCl? All right, this should be a pretty simple dilution. Throw it into your calculator. You're going to do 250 times 0.025 divided by 0.1. That would be using the millimoles. You can convert your 250 milliliters to 0.25 liters if you want to keep it that way, but you're going to multiply volume and molarity. That's going to give you moles. You're going to divide your moles by this other molarity. That's going to give you the volume. So I don't want to do this math. I'm not going to do it mentally. I'm just going to, I think when you multiply that through 250 times 0.025, well, 25 times 25 is 625. So I'm going to go with this 62.5 because that looks the right. But again, throw it into your calculator, especially in the free response. So just throw it into the calculator. Question 16, I'm saying C. Didn't do the math, just kind of taking a guess. Oh, look at that. Wahoo! All right, question 17. A 500 ml aqueous solution of Na3PO4, sodium phosphate, molar mass 164 grams per mole, was prepared using 82 grams of the solute. Look at that, looks like golf. Man, if that was my test, you guys would give me such a hard time with it. What is the molarity of Na3PO4 in the resulting solution? All right, so we're using 82 grams. It's got a molar mass of 164 grams per mole. So that means we're using 0.5 moles, and we have 500 mLs of solution. That's 0.5 liters. So 0.5 moles divided by 0.5 liters, that's going to be 1 molar. All right, choice D, 1 molar. I hope we get a question that easy on the AP exam. That would be incredible. All right, so it should be choice D, 1 molar. Wahoo! Question 18. How many grams of NaCl, molar mass 58 grams per mole, are needed to prepare 100 mLs of a 0.25 molar NaCl solution? All right, 100 mLs means 0.1 liters. If we multiply 0.1 liters by 0.25 molarity, moles per liter, that means 0.025 moles of NaCl. So that's our moles. We can do moles times molar mass, so 0.025 times 58. I would throw that into a calculator, 0.025 times 58. So it's a quarter of 58, and 58 is pretty much 60. So it's going to be like a quarter of that. So it's going to be around 15. But not only is it a quarter, it's like by a factor of 100. I don't know. I've lost. I'm going to guess. See, if we just had a calculator here. I don't have a calculator on me. Again, 0.025 times 58 should give you your answer. Let's see what it is. Question 18. And it was the 1.5 grams. So that should be an easy calculation. I just didn't have my calculator handy. All right, question 19. Ooh, we got methanol, we got water. We got their molar mass, all right? The water is definitely smaller than the methanol. We got their density, we got their boiling points, all right? And we have their structure. Ooh, we got some hydrogen bonding going on both. This is gonna be a dipole, and this is gonna be London dispersion forces. When methanol and water are mixed together, they form a homogeneous mixture. Based on the information in the table above, which of the following would be the best procedure for separating a mixture of methanol and water? Homogeneous mixture, they're both liquids. All right, how do we want to separate them? We want to exploit those boiling points. We want to get it to some temperature above 338, but not quite to 373. So that way the methanol will boil, the water will stay behind. That is distillation. That is choice B. So question 19 should be choice B. Distillation, yep, nailed it. Woohoo! Question 20, which of the following methods is most appropriate to use to determine the number of different colored components in a sample of black ink? We did this, lab class, definitely. We're using the paper chromatography, using different solvents with a range of polarities as the mobile phase. All right, we've never done column chromatography. I don't think many schools have done column chromatography.
don't fall for that just because of chromatography. We do paper chromatography, right? The little strips of paper. So question 20, it is choice D. There we go, wahoo. 21, oh, look at that. Here is the readout from a paper chromatography lab. All right, we got solvent A, solvent B, solvent C, solvent D. So in A and D, they're staying pretty close together. B and C, they're spreading out a little more. We got the solvent front the whole way. The diagram above shows thin layer chromatographies of the same mixture of two compounds. Based on the chromatograms, which solvent would be the most effective at separating the two compounds if the same stationary phase is used for column chromatography? All right, so we want the one, I believe, that they're gonna spread out the most. All right, so if we're gonna take this and do it in the column chromatography, we want the most dramatic difference between the two. So I'm gonna say solvent C. All right, let's see what we get for question 21. Solvent C, and again, what they are asking you here is which of these is the best to separate the two, and you can see that in A and D, they're not even separated, and B, there's only a little bit of separation. So choice C is the correct answer there. Wahoo! 22, 2/3 of the way through. Thank you for staying with me, okay? Thank you for bearing with me as I say, wahoo, after every question. All right, maybe I'll get one wrong in this next set and I won't get to say it. All right, methanol, CH3OH, dissolves completely in water to form a solution that does not conduct electricity. That's important. Which of the following diagrams best shows the major type of attractive forces that exist between the particles in the solutions? All right, so here in choice A, we actually have ions. So that discredits it, right? Because the ions would mean that we are able to conduct electricity. This would actually be an acid base where the hydrogen and the oxygen actually breaks off and joins the water. Not very common, all right? That does occur in our carboxylic acids. In the organic molecules, it doesn't often happen in the alcohols. So it's not choice A. It's not choice B either, because again, we have the charges. Ooh, choice C, look at that. Hydrogen bonding between the hydrogen of water with the oxygen of the methanol. I like choice C. Choice D, do I like it? It's oxygen attracted to another oxygen. No, they would repel, right? They're not going to like that. They're both slightly negative, so they're going to push away. It's going to be choice C for question 22. All right. Just sitting at your desk at home, say it with me. Wahoo! Question 23. Conductivity with increasing mass of unknown solid added. So we're getting a direct relationship. So if you add more solid, it becomes more conductive. A student adds a 1 gram sample of an unknown brittle. Ooh, what are things that are brittle? Typically lattices, correct? Brittle solid to distilled water, stirs the mixture, and then measures its conductivity. The student repeats this process with more samples of the unknown solid and then produces the graph above. Which of the following statements about the graph and the properties of the solid is correct? The increase in conductivity indicates that the unknown is an ionic solid that dissociates into ions when it dissolves in water. I like that. Ionic compounds conduct electricity. None of the other solids do when they dissolve in water. All right. The increase in conductivity indicates that the unknown is a network covalent solid. Nope. Straight line, unknown solid is infinitely soluble in water. I mean, kind of, but I don't think that that's, explaining why. It's still like choice A. The straight line plot indicates that the unknown solid has a very low solubility in water. Definitely not. All right. So I like choice A. In theory, yeah, it is. So it could be C. I wouldn't be too thrown off if that was the choice they get. But the increase in conductivity indicates that the unknown is an ionic solid that they associate with ion. I like choice A. I'm going with choice A for question 23. What did they go with? Oh God. Choice A. Woohoo! All right. If it was a solid that does not dissolve, then yeah, you would not get that conductivity. So that is something that we could ask you. Question 24. Ooh, diagram 1, we got KCl. Diagram 2, we got KCl. I'm already liking diagram 1 over diagram 2. I'm gonna bet we're gonna be asked why.
All right, which of the diagrams above best represents the interactions that are responsible for the relatively large solubility of KCl crystals in water, and why? All right, KCl crystals, lattice, ionic compound, positive and negative, right? They are ions, they have those fixed charges. They do not have partial charges. Those are for polar molecules, not ionic compounds. So it's going to be diagram 1. All right, diagram 1, because strong ion dipole interactions between KCl and water help to dissociate the solute. Sounds good. Diagram 1, because strong London dispersion forces. Nope, I'm going with choice A. All right. Question 24, choice A. Wahoo! All right, 25. Which of the following best explains what happens as photons of visible light are absorbed by dye molecules? All right. Just remember from that spectroscopy video, visible light and UV, those have to do with electronic transitions. The infrared has to do with the vibrations, and the microwave has to do with the rotations. So that might be coming up in this question. So it's a good thing we reviewed that. Certain electrons in the dye molecules move to a higher energy level, with the difference in energy between the lower and higher energy levels being the same as the energy of the absorbed photons. I like that. I like choice A. Choice B, certain chemical bonds in the dye molecules begin to bend and stretch, with the difference in electricity between the lower and higher vibrational states being the same as the energy of the absorbed photons. That would be like for infrared radiation, but not for our visible light. The dye molecules begin to rotate faster in certain modes. No, not rotation. Certain covalent bonds in the dye molecules begin to break and reform, with the bond energies of the bonds being the same as the energy of the absorbed photons. I like choice A. I did not like B and C. If I chart it all wrong, then it's probably going to be choice D, so that's going to be embarrassing. Ooh, choice A. Wahoo! All right, so again, visible spectroscopy, ultraviolet, we are moving electrons to higher energy states, which is something we've seen before in electronic structure. It's nothing that we shouldn't be unfamiliar with. All right, question 26. Ooh, intensity of transmitted radiation, and we have the wavelengths. The infrared spectrum above represents the absorption of certain wavelengths of radiation by molecules of CO2. Which of the following best explains what occurs at the molecular level as the CO2 molecules absorb photons of the infrared radiation? The atoms in the CO2 molecules increase their vibration as the bonds between the atoms bend and stretch. I like that's infrared radiation. The molecules of CO2 increase the energy of their rotational motions. Well, that's more like the microwaves. The electrons in the valence shells of the atoms in the CO2 molecules are promoted to higher electronic energy levels, UV visible light. All right, but we're dealing with infrared. The bonds between the atoms in the CO2 molecules are continuously broken and then reformed. I'm going with choice A for this one. You will see these IR graphs. And again, if you take organic chemistry, I don't know why they're trying to force it right now. All right, but it's the IR, it's the vibration. So for question 26, it should be choice A. And it is choice A. Wahoo! Let's move it along. We got 7 questions left. Okay, we have an alcohol forming a carbonyl group. The R's represent just chains of carbons, doesn't matter, all right, hydrocarbons. So we're just going from an OH bond to a double bond O. All right, so again, this is where having a little bit of organic background does help us. One type of organic molecule can be converted into another type of organic molecule through an oxidation reduction process, as represented in the diagram above. Which of the following best explains why infrared spectroscopy is an appropriate method to confirm that the product contains a carbonyl? Again, I don't know why they are pushing this organic chemistry on you guys when they've made moves to have less organic chemistry, all right? But what they're going to go here, what they're trying to get you to think is if you do infrared spectroscopy, the carbon oxygen bond and the oxygen hydrogen bonds, they will absorb different amounts or different wavelengths, I should say, of infrared radiation than the carbon double bond oxygen. So that's where they're trying to lead you with this question. All right, so let's look through the choices. Question A, the absorption of infrared radiation causes the non-binding electron on oxygen to transition into a higher electronic energy level. Nope, that would be the UV vis.
Choice B, the absorption of infrared radiation leads to an increase in molecular vibrational level associated with the stretching of the carbonyl. That sounds good, right? Because we have the vibrations, it's stretching. Choice C, the absorption of infrared radiation causes the electrons in the pi bonding to transition to a higher bonding energy level. Nope. Choice D, infrared radiation leads to an increase in the molecular rotational level associated with the carbonyls. All right, again, rotational is microwave, so this one's going to be choice B. All right, so 27, we are saying it's choice B, and it is. Wahoo! All right, I don't think that this will be a big topic, but it's a good thing that we reviewed it now in this video. All right, just correlate those three together. UV visible spectroscopy, electron transitions, infrared, vibrations, and microwave going with rotations. So just kind of memorize that, and then you don't have to worry about it because it's never going to be anything different from that. Question 28, electromagnetic radiation with a maximum wavelength of 540 nanometers, 5.4 times 10 to the negative 7 meters, is needed for the study of the photoelectric effect in potassium atoms. What is the appropriate frequency that corresponds to this wavelength? All right, so the speed of light, 3.0 times 10 to the negative 8th, will equal 5.4 times 10 to the negative 7th times it. Since that's a really small wavelength, we're going to have a fairly high frequency. And I'm going to go, since it's going to equal, since the 10 to the negative 7th times whatever the frequency is going to equal 10 to the 8th, I'm going to go with this 10 to the 14th just because it's in the appropriate range. I did not do the math. I am guessing for 28 that it's going to be choice D. And it is choice D. Wahoo! 29. In an experiment on the photoelectric effect, a photon with a frequency of 7 times 10 to the 14 seconds inverse was absorbed by a sample. What is the approximate energy of the sample? All right, so we are doing that E equals h nu. Planck's constant is 6.626 times 10 to the negative 34th. If we multiply that by 10 to the 14th, we're looking at something about 10 to the negative 20th. Going through my choices, the closest is 5 times 10 to the negative 19th. Did I not in class tell you 10 to the negative 19th, always visible light? All right, I'm saying for 29, it's going to be choice A, and it is choice A. Wahoo! 4 questions left. Ooh, we have a chart. Ultraviolet, visible, infrared, 7.5 times 10 to the 14th to 3 times 10 to the 16th. Infrared, 3 times 10 to the 11th to 4 times 10 to the 14th. All right. The frequency and energy ranges of photons in some parts of the electromagnetic spectrum are given in the table above. Which of the following could be the energy of a photon in the visible range? All right, so think about it. The visible range, it's Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So infrared is just beneath it, ultraviolet just above it. So it's got to be in this 10 to the 14th range, its frequency. All right, so its joules are going to be in that 10 to the negative 19th range. And it's got to be above 3, below 5. I'm going to go with 4 times 10 to the negative 19th, choice C. All right. And it was choice C. All right. Wahoo! Question 30, we got right. 31. All right. Okay, so we have a graph of the absorbance. The absorption spectrum of a certain red dye is shown above. If a student analyzing the same concentration of this dye neglected to wipe fingerprints off the cuvette before placing it in the spectrophotometer, how would the absorption curve be affected? All right, neglected to wipe fingerprints. I feel like that is going to have less light go through, so it's going to seem like there was a higher absorbance. All right, so the peak of the curve would be higher because more light would be absorbed. Ooh, if they're saying the peak of the curve, all right, yeah, that sounds right, because if it seems like more light would be absorbed, the peak would be higher. The peak of the curve would be lower because less light was absorbed. The peak of the curve would be shifted to the left because less light would be absorbed. The peak of the curve would be shifted to the right. All right, I don't think it's going to shift it left or right because that's the wavelength that it gets absorbed at. I think it's going to be the peak. I think for question 31, it's choice A. Let's see what they say. Ooh, choice A. Wahoo!
All right, the peak is getting higher. It's not changing the fact that the certain dye absorbs at the same wavelength, but because of that smudge, it scatters some of the light. So not as much light as should have reaches the detector. So we think we had more being absorbed than actually was being absorbed. All right, so that's what was happening in question 31. 2 questions left, 32. A student measures the absorbance of a solution containing iron thiocyanate ion using a spectrophotometer. The cuvette used by the student has 2 frosted walls and 2 transparent walls. The student properly orients the cuvette so that the path of the light goes through the transparent sides of the cuvette when calibrating the spectrophotometer. How will the measured absorbance of the iron thiocyanate be affected if the student incorrectly orients the cuvette so that the path of light is through the frosted sides of the cuvette? Well, that's going to scatter a ton of light. All right. So the measured absorbance of the solution will not be affected. No, it's definitely going to be affected. The measured absorbance of the iron thiocyanate solution will be higher than the actual absorbance. I'm thinking that's what's going to be happening. The measured absorbance of the iron thiocyanate solution will be lower than the actual absorbance. Well, that doesn't make sense because the light's not getting through. The effect of the measured absorbance of iron thiocyanate solution depends on the concentration. I'm thinking 32, choice B. 32, choice B. Woohoo! Got it. Last question, 33. A student uses a spectrophotometer to analyze a solution of blue food dye. The student first rinses a cuvette with distilled water, then the student adds the blue dye solution to the cuvette, forgetting to rinse the cuvette with the blue dye solution first. The student places the cuvette in the spectrophotometer and measures the absorbance of the solution, assuming that some distilled water droplets were still in the cuvette when the blue dye solution was added. How would the measured absorbance be affected? So if we accidentally diluted the solution, we're going to get a lower absorbance. The measured absorbance would be too low because the distilled water was left in the cuvette with slightly dilute solution. I like that, choice A. All right, just scanning through. Too low because optimal wavelength, not choice B because the optimal wavelength doesn't change. Choice C. Too high, no, we're saying it's going to be too low. Too high for choice D. So question 33, we are saying it is choice A, and it is choice A. Wahoo! I know that's exhausting. We'll do another video on the free response questions, but not right now. All right, hopefully you did well with these questions. You're seeing the same kind of themes. Just be careful. Things that came up a lot in these practice questions, the UV vis, infrared, and microwave spectroscopy, that came up a few times, so that's a good thing to kind of have in your back pocket. The covalent network versus the molecular network, all right? The covalent network solid has the covalent bonds. The molecular solid just has the London dispersion forces. We saw in action that phrase polarizability, so that's important. We also saw those diagrams, lots of diagrams in these questions, the way that they represented the intermolecular forces. All right, so lots of good stuff in here. Hopefully you made it through to the end. And if you see any of these things on the actual AP exam, hopefully you feel comfortable with it and you're like, I'm glad I did that Unit 3 progress check, okay? Because we know that this unit traditionally has the most questions on the exam.